Here's another example we should quickly evaluate together. Find the Thevenin equivalent of the circuit to the right of the line CD. Where is the line? This is line CD, okay? Of the right of the line CD to the left of the line AB. You can see we have AB here, and use the results to find the value of V1. So this is V1 that we're looking for. Okay, now what are we supposed to do? We are supposed to just draw a line across AB and then draw a line across CD. To the left of AB, we would find the equivalent circuit, and to the right of CD, we would also find the equivalent circuit, and then we'll combine everything together with these 0.5 kilo ohms, and then we can find our V1 and find everything that is missing in the circuit. All right, let's get started. So starting with CD, okay, so we draw a line on CD, and when we do that, this is exactly all we have left. And when we kill all the sources, there is only one source, and that is the current source. When we kill it, it simply means we are going to have an open circuit. When we have an open circuit, no current is going to flow through this particular branch, okay? And we can easily find our R equivalent when we do that. How do we find our R equivalent? You will notice that 1 kilo ohms is in series with 1 kilo ohms. These guys are in series, so we have 1 plus 1 that gives us 2 kilo ohms. If we do that, we will notice that whatever we obtain as the equivalent of this series, 1 kilo ohms and 1 kilo ohms, would be in parallel with these 2 kilo ohms. So we have 2 parallel 2 kilo ohms, okay? And that will give us 2 times 2 divided by 2 plus 2. And that eventually ends up to be 1 kilo ohms again. And then that 1 kilo ohms will again be in series with this 1 kilo ohms, and that gives us another 2 kilo ohms. And that 2 kilo ohms that we have eventually will now be in parallel with these 6 kilo ohms here. All right, so 2 parallel 6 kilo ohms will give us 2 times 6 divided by 2 plus 6, and that will give us 12 divided by 8 kilo ohms at the end of the day. So that's just a dry run of what's going to happen. So let's quickly go through it together right away. So this entire circuit here, you will see that these guys are in series. That is why we have 1 plus 1 here. They are in series, and that series combination would be in parallel with these 2 kilo ohms. When we do that, we would obtain 1 kilo ohms at the end of the day, just like I mentioned earlier. That 1 kilo ohm will then be in series with these other 1 kilo ohms here, and that would give us 1 plus 1 again. So, and that series connection would be in parallel with this parallel connection. Will be in parallel with these 6 kilo ohms. So that is R 1 plus 1 in parallel with these 6 kilo ohms. And that gives us 6 multiplied by 2 over 6 plus 2. And that gives us 12 over 8. And that gives us 1.5 kilo ohms. That 1.5 kilo ohms becomes our R equivalent, and that will be our R Thevenin for this right hand side. The next thing we'll do will be to open the circuit terminals, this CD. When we open these circuit terminal, what do we have? We're going to have open circuit voltage. We are going to have open circuit voltage. The open circuit voltage will be equal to V Thevenin, the Thevenin equivalent Thevenin voltage. So VT equal to VOC, which will be equal to current multiplied by the entire resistance, the equivalent resistance in the circuit. The equivalent resistance will be the resistance representing all these resistances in the circuit. And to find the voltage, it will just be the resistance multiplied by the current available, and that gives us 4 milliamperes multiplied by 1.5 kilo ohms, and that gives us 6 volts. So our V Thevenin, which is equal to our V open circuit, will be equal to 6 volts. So that's all about the right hand side of line CD. Now we want to look at the left hand side of line AB. Don't forget that now that we have our R equivalent and our T Thevenin, everything we have on the right hand side of this CD can be represented with a voltage source and a resistance. That voltage will be the open circuit voltage, which will be 6 volts, and the resistance will be equivalent resistance, which will be 1.5 kilo ohm. So to the right of CD, we just have one resistance, 1 volt, voltage source here, and then we'll move on. That's all. We just have to write that. We have reduced this complex circuit to that small Thevenin circuit. Now to the left of AB, this is what we have. The first thing we want to do is to kill the sources. There are two sources. We have the voltage source and then we have the current source. When you kill the current source, you open the circuit. When you kill a voltage source, you short the circuit. So that's exactly what we are doing. If we do that, our R Thevenin for this left side of AB will be equal to 2 kilo ohms, because that's the only thing we have here. And when that happens, the next thing you want to do is to open circuit this terminal AB. When you open circuit the terminal AB, we are going to have our VOC. And what would our VOC be? It will be equal to our V Thevenin. So the voltage across 2 kilo ohms will be equal to 2 kilo ohms multiplied by 1 milliampere, which is the current passing through that, and that gives us 2 volts. So there is 2 volts here. But from this particular configuration, you will notice that the terminal of this right hand side here is positive. As you can see here, this is positive here, so that means the terminal here is positive, and then this is negative. And we mentioned earlier that when we have a situation where there are 2 voltages in a circuit and that are connected in series, and if the positive end of one of the voltages is connected to the negative end of the other voltage, it simply means it is called series aiding voltage. It means they are called series aiding voltage sources. In cases like that, the net voltage will be the addition of the voltages. So we have 2 volts here, we have 12 volts here. Adding those 2 voltages together will be the equivalent voltage in this particular circuit that will be seen by this VOC. So our VOC will be equal to V Thevenin, which will be equal to 14 volts, adding 12 to 2 volts here. So the reason that is the way it is because this terminal is positive here. Automatically what we have here is positive. This terminal is positive here. So, and then this will be negative, and then positive to negative will mean that current is only allowed to flow in one direction. That's what it simply means. So they are aiding one another. So 12 plus 2 volts will give us 14 volts. So if V Thevenin 2 is 14 volts and our RT2 is 2 kilo ohms, it simply means we have converted this particular left hand side of AB to the Thevenin equivalent. We have the V Thevenin, we have the R Thevenin. We have also converted the right hand side here to Thevenin equivalent we have as calculated earlier. So let's go ahead and bring everything together. So if we bring everything together, what we would have is this first equivalent circuit we obtained is 1.5 kilo ohms and 6 volts. We bring that here to the right hand side of CD. Everything put together, we obtain this Thevenin circuit for it. To the left hand side of AB, everything to the left, we obtain this Thevenin equivalent for it. And then we still have our 0.5 kilo ohms and our V1 here. So you can see what we have here is a very simple circuit that we can easily work with. The equivalent resistance for this circuit therefore will be equal to the summation of this resistance plus this resistance plus this resistance, because they are now all in series, and that gives us 2 plus 0.5 plus 1.5. That's 4 kilo ohms. And since we are looking for V1, we can easily say that V1 is the voltage across this 0.5 kilo ohms, and that's going to be very easy to find. All right, we know our V source. How do we find our V source, by the way? From what you can see here, we have 2 series voltages, voltage 1 and voltage 2. Again, you will notice that these 2 voltages are actually, from the look of things now, they are the positive end of one voltage is connected to the positive end of the other voltage. And this simply means that they are series opposing voltages. For series opposing voltages, the net voltage can be obtained by subtracting the smaller voltage from the bigger or larger voltage. So if you take 6 from 14, what you're going to have left is 8. So the effective voltage in this particular circuit will be 8 volts. So the voltage source here will now be 8 volts, 14 minus 6. So to go ahead and find V1, we apply the voltage divider rule. Since we have plus here and negative here, what we would have left would be minus V1 would be equal to Vs, which is now 8, multiplied by the resistance across V1, which is 0.5 kilo ohms, divided by the equivalent resistance, which is 4 kilo ohms. Don't forget, it's going to be minus V1 because of this polarity. Do you see this polarity here? Okay, so it's going to be minus V1, all right, equal to 8 multiplied by 0.5 kilo ohms divided by 4 kilo ohms. If you multiply both sides by negative, it becomes V1 equal to minus 8 multiplied by the ratio of the resistances. If you find out what that is, by simple arithmetic operations, it gives us minus 1 volt. Okay, so note the negative sign comes from the direction of V1 voltage as given in the problem. So this direction, that is where this negative came from, and that is why we had to write minus V1 at the beginning that eventually converted everything to negative sign. This example is a very important example. It's critical, it's important. Pay attention to it, check it out over and over and over. If there are questions in your mind, if there are doubts in your mind, reach out to me and I will try to clear your doubts and help in any more ways I can help in addition to this explanation. So you can reach out to me in the comment section right below this video, or you can reach out to me via any other means necessary. So we should quickly talk about theoretical sources. An ideal voltage and current source can theoretically deliver infinite power. So you can see we have a voltage source, we have a resistance here, or a load resistance, and you can see our load current flowing through the load resistance. So our power would be equal to V squared over R. In this case, Vs squared over RL. As RL decreases, as we decrease the value of this load, our PL tends to infinity as RL decreases to 0. So the smaller this resistance, the higher the power. That is what we are talking about. Okay? Then here, if we look at it, considering the current source, PL will be equal to I squared R. In this case, our I will be the source current, so we have IS squared multiplied by RL. This tells us that as RL increases, if we increase RL, our power would also increase. So as RL, from this particular equation we have here, as RL increases to infinity, our power would also increase to infinity. This is simple arithmetic operations, by the way. As this one becomes smaller, that simply means that the value of this ratio will become bigger. So PL tends to infinity. Again, simple arithmetic here. As RL becomes bigger, it simply means whatever you multiply by it also becomes bigger. So PL keeps growing and tends to infinity as RL tends to infinity. This is what happens when we have theoretical sources. Now, when we have practical sources, what happens? Are we going to deal with practical sources just like we would deal with theoretical sources? If the answer is yes, let us evaluate it together. If it is no, we will find out now. In reality, there are always resistive drops associated with practical voltage and current sources. These can be modeled using the Thevenin and Norton equivalent circuits respectively. So what we see here, you can see we have Vs, so there would always be a resistive drop associated with this voltage source. So there will be Rs here. If there's Rs here, we also have our load resistance here, and we have our current flowing through the load resistance here. So in that particular case, our PL will therefore be equal to, it will be equal to V squared over RL. Let us quickly evaluate this together. Now you can see we have a resistor here, which is Rs, and then we have another resistor here, the load resistance, and we have our IL. So that simply means there should be a voltage drop across this RL, which will be referred to as VL. So now we want to find the power that is consumed by RL. So that PL will be equal to VL squared divided by RL. Okay, in this case it will become VL squared divided by RL. But we don't know our VL. So we're going to try to find our VL from this circuit using the voltage divider rule or any other rule that we can use. Okay, first of all, I want you to know that we have v squared over RL. That RL is what we are bringing out here. So v squared over RL is here now. This is the RL represented as 1 over RL. V squared over RL is the same thing as V squared multiplied by 1 over RL. So we have VL squared multiplied by 1 over RL. The 1 over RL is brought out here. So everything you see right inside this bracket represents the value of VL. And of course, we have to include the squared here. So how did we obtain VL to be these values? VL is going to be the voltage across this resistance, and to find that voltage we can use voltage divider. So VL will be equal to the source voltage, which is Vs, multiplied by the resistance of VL, which is RL, divided by the equivalent resistance in the circuit, and that's going to be Rs plus RL. So the equivalent resistance in the circuit is Rs plus RL. That's what we have here. So our VL would therefore be Vs multiplied by RL over equivalent resistance. And that's exactly what is here. All brackets squared, then multiplied by 1 over RL. So if we expand this becomes Vs squared, RL squared, all divided by RL plus Rs squared. So this RL will cancel one of the RLs here. So we're going to be left with just one RL at the end of the day. So that is why we have these. That is why we have this value here. This is simple mathematics. Once you can find your VL, the rest is just simple mathematics, and we can move on. So you will notice now that for practical sources, which is as a result of the fact that there has to be at least a small resistive drop associated with the voltage source, no matter what happens. The resistance cannot be totally zero, okay, in practical sense. So when we have the situation and we say RL tends to 0 this time around, initially when we had the theoretical source, we said that when RL tends to 0, PL tends to infinity. But in this case now, when RL tends to 0, our PL will tend to 0. PL will tend to 0. Again, when we look at the Norton circuit, we have a small resistive drop, and then we have our load resistance. Since we are looking for the power across L, it will become IL squared multiplied by RL. So that RL is what we brought out here. So everything you see in this bracket represents our IL. How do we find our RL? We use current divider. The equivalent resistance would actually be, these guys are in parallel, Rs and RL are in parallel. So this equivalent resistance will be Rs multiplied by RL divided by Rs plus RL. That's exactly why we have RL plus Rs here. So we have Rs multiplied by RL right at the top here. Okay, so that is the equivalent resistance. And since we are looking for IL will be equal to RL multiplied by the source current multiplied by Rs multiplied by RL, all divided by RL plus Rs. When you carry out that simple arithmetic operation, you will be left with what we have in this bracket. Again, when RL tends to infinity in this particular case, PL will tend to 0, as against what we had when we have the theoretical case. So pay attention to these practical and theoretical sources, and let's see exactly how everything plays out, because we will use them in some other analysis as we go on. Here is another example that is important regarding all the discussions we've had. An automobile battery in a poor state of charge has an open circuit voltage of 11.5 volt DC, and when loaded by the starter motor, which we model as 0.8 ohms resistor, supplies 10 volt across the starter motor terminals. Determine the power delivered to the load and the power being dissipated internally in the source resistance under these conditions. So the first thing we try to do is to draw out the circuit. An automobile battery in a poor state of charge has an open circuit voltage of 11.5 volts. So you can see we have the open circuit voltage 11.5 volt DC. It is DC. That is why you can see we are using two bars here, a smaller bar and a bigger bar. And you can see our polarities, plus and minus here. So we have 11.5 volt DC. And when loaded by a starter motor, which we model as 0.8 ohms resistor, supplies 10 volt across the starter motor terminals. Okay, so you can see we have, this is a starter motor, this is the load. So when loaded by the starter motor, so you can see our RL is 0.8 ohms, and then you can see the voltage across the starter motor, which is 10 volts across the 0.8 ohms. Okay, so what you will notice is that we are going to have a resistive drop, a small resistive drop in real life, in real applications, and then there's going to be a voltage across a small resistive drop too. The question then says, determine the power delivered to the load, that is PL, and the power being dissipated internally in the source resistance. So you can see we have an internal source resistance here under these conditions. Okay, now the power delivered to the load PL will be equal to VL squared over RL. We have the VL, which is 10 volt has been given in the question. So V squared will be 10 squared, that is 100. RL is 0.8 given to us already in the question. That is why we have PL equals 100 divided by 0.8, and that gives us 125. Having done this, the next thing we want to find out is to use voltage division to calculate the value of RS. So we are lucky enough, we know the RL now, and then we also know the other voltage, the voltage source here. Okay, so voltage division says that if you are finding the voltage across RL, if you are trying to find the voltage across this 0.8 ohms resistor, which is your VL, our VL will be equal to the V source, which is 11.5, multiplied by the resistance RL of this VL, which is 0.8 in this particular case, divided by the equivalent resistance in the circuit. The equivalent resistance in the circuit will be RS plus 0.8 because they are connected in series. So if we have that, we have everything documented. The VL is given as 10, VS is 11.5. The only thing missing that we don't know is the RS. The only thing missing that we don't know is the RS. So once we arrange this, we can easily find our RS. And that would give us 11.5 multiplied by 0.8 divided by 10 minus 0.8. Altogether, we would obtain 0.18 ohms by just applying simple arithmetics to this expression here and rearranging to find RS. So we obtain RS to be 0.12 ohms. And the question says we should determine the power delivered to the load, which we have found, and the power being dissipated internally in the source resistance. The power dissipated in the source resistance will be equal to the power consumed or absorbed by the source resistance. And that's what we're going to quickly find right now. That power will be equal to Vs squared divided by Rs. We know Rs already from our calculations to be 0.12. We know our Vs already, okay? And this Vs will be, we know our source voltage, and then we know the 10 volts across the load resistance here. The only volt we don't know is this Vs, and this can easily be calculated. So how do we then get our Vs? You can apply KVL to this loop. You can apply KVL to this closed path. When we have our path drawn clockwise, current flowing clockwise, then we can say that plus Vs, because that's Vs at positive side, we can say plus Vs plus 10 minus 11.5 is equal to 0. So Vs plus 10 minus 11.5 is equal to 0. If you make Vs the subject of the equation, it becomes Vs is equal to 11.5 minus 10. And that's exactly what we have here. So instead of writing Vs, we write 11.5 minus 10. When you square that, you have a value, then divide that value by 0.12. That gives us 18.75 watt. So the power dissipated internally in the source resistance under these conditions given in the question will be 18.75 watt, and the load power will be 125 watt. Okay, take your time, go over this example again and again, and get the best out of the concept shared. Let's take one more example. A 500 milliampere fuse is located in the wire connecting a power supply to its load. If the power supply has an open circuit voltage of 100 volt DC and a source resistance of 30 ohms, what is the range of acceptable load resistances that will not cause the fuse to blow? Okay, the first thing we try to do is to draw out the circuit. When you draw out the circuit, this is what you're going to have. A 500 milliampere fuse is located in the wire connecting a power supply to its load. So this is the power supply here. If the power supply has an open circuit voltage of 100 volts, so this is the power supply, and then you can see we have the voltage of 100 volt here. It's a DC voltage, so you can see it's a DC symbol we have here. And a source resistance, you can see we have RS, the source resistance of 30 ohms. This is the source resistance of 30 ohms just after the voltage. What is the range of acceptable load resistance? You can see we have a load resistance whose value we do not know here. So we label that as RL. What is the range of acceptable load resistances that will not cause the fuse to blow? All right, so that simply means that from what they said, we have a 500 milliampere fuse, which is located in the wire connecting a power supply to its load. So the fuse is between the power supply and the load. This is the load, this is the power supply. So the fuse is somewhere in between here before the load. Okay, the rating of the fuse is 500 milliamperes, which is the same thing as 0.5 amperes. So it simply means that we are looking for the acceptable load resistance that will not cause the fuse to blow. For the fuse not to blow, the current passing through the load should not be greater than 0.5 amperes. The current passing through the load should not be greater than the current of that fuse. If the current is greater than the current of the fuse will automatically blow. So the current passing through this load should be less than the fuse current, which we know as 0.5 amperes or 500 milliamperes. So we can say that current passing through current will be equal to the source voltage, which is 100, divided by the equivalent resistance in the circuit. The equivalent resistance in the circuit will be 30 plus RL, and that's exactly what we have here. And whatever we obtain when we divide 100 by this addition of 30 plus RL, whatever we obtain as our I, it should be less than 0.5. So what you will find out is that we have an inequality expression here. So if we rearrange this inequality expression, we have 100 divided by 30 plus RL less than 0.5 amperes. If we rearrange that, you will find out that our RL is greater than 170 ohms. So this simply means that our RL has to be chosen, has to be designed, has to be selected in such a way that it has to be greater than 170 ohms. If RL is less than 170 ohms, if RL is not greater than 170 ohms, or if we say it in another way, if RL is less than 170 ohms, this simply means that more current that is higher than 0.5 amperes will pass through it. And if that happens, this fuse will blow. And we don't want that to happen according to the question. So this is the best design we can have for our RL. This is where we'll end this lesson. I hope you have enjoyed it. I hope you have gotten the best out of the concepts shared in this lesson. I will encourage you to subscribe to this channel in case you have not done so. And if you have done so, give this video a thumbs up if you like it. And don't hesitate to let me know what you think about some of the examples, some of the explanations, some of the concepts discussed. Whatever you think about this video that you want me to also pay attention to, please drop them in the comment section. I would really love to read them. I would love to read from you. Thank you for watching. Thank you for learning. I'll see you in the next lesson.